Video platforms hide their complexity perfectly. As a user, you open an app, press upload, and the video appears for the world to watch. If you were building this system from scratch, the instinct is to treat that video file exactly like a profile picture or a text post. You send the file directly through a standard API server. But a standard API server is designed to process lightweight text requests in milliseconds. When a 300 megabyte video file hits that exact same server, it monopolizes the network connections and memory. Every other user trying to load a web page or post a comment is suddenly blocked, waiting in line behind a massive file upload. To understand how to actually solve this, we have to isolate the problem. For this design, we are going to strip away the recommendation algorithms, the advertising networks, and the comment sections. Designing a global video platform requires an entirely different approach from standard application design. It is a continuous battle against hard storage limits and overwhelming bandwidth constraints. Let's look at the baseline math. Assume we have 5 million daily active users. If just 10% of those users upload an average 300 megabyte video each day, that generates 150 terabytes of raw data. That is the physical storage footprint added to the system every single day, requiring a massive, scalable database infrastructure just to hold it. But storing the video is only half the equation. Delivering those videos back out to millions of viewers generates astronomical network egress bills. This chart details the on-demand pricing for data transfer from Amazon's cloud delivery network. At an average cost of 2 cents per gigabyte, serving those videos to 5 million users costs $150,000 every single day. This math dictates our entire strategy. We have to build an architecture specifically designed to route this heavy, expensive video traffic away from our core processing servers and onto highly optimized edge networks. The foundational rule of video architecture is strict. Heavy media files must never touch the core API servers. To enforce this, we split the infrastructure into 2 entirely separate domains, each optimized for completely different tasks. This diagram shows that high-level separation. Everything lightweight goes to the API servers, while the streaming video is isolated to the Content Delivery Network, or CDN. The right side of this system is the control plane. These API servers handle logic, user signups, and metadata updates, the text, the titles, the tags. They process tiny requests with lightning speed. The left side is the media plane. This is the industrial pipeline. It consists of massive blob storage systems and CDNs built specifically to hold and transport heavy byte payloads. By strictly isolating the media plane from the control plane, a massive video upload cannot suffocate the fast, lightweight components powering the user interface. When an upload begins, the device first contacts the API server to request a pre-signed URL. This URL acts as a temporary, secure permission slip, allowing the client to bypass the API entirely and upload the heavy video file directly into original blob storage. But a raw video file straight from a smartphone might be recorded in 4K at 60 frames per second. If we try to stream that massive file to a user on a weak 3G mobile network, it will buffer endlessly. To solve this, the original file is passed to transcoding workers. These are heavy compute servers dedicated to compressing and converting the video into formats optimized for different devices. This flow diagram illustrates the transcoding pipeline. Using a directed acyclic graph, or DAG, the system processes the video in parallel, splitting the raw file into multiple resolutions, like 1080p, 720p, and 480p, and then pushes them into a transcoded storage bucket. We intentionally burn expensive compute power and storage capacity up front during this transcoding phase to guarantee cheap, seamless playback for viewers later. While the video file uploads to storage, the user's device sends a parallel request to the API server containing the video title, description, and thumbnail. This diagram shows the API instantly writing that lightweight text into the metadata database and cache. Here lies a severe timing mismatch. Saving the text takes milliseconds, but the transcoding servers might take an hour to process a long video. The user cannot be left staring at a loading screen waiting for the processing to finish. To decouple these timelines, we use asynchronous coordination. Once the transcoding servers finish their heavy lifting, they drop a simple event message into a completion queue. A separate set of workers, called the completion handler, constantly monitors that queue. It grabs the success message and updates the metadata database, officially marking the video with the final, playable CDN links. These asynchronous message queues act as essential shock absorbers. They allow a slow, heavy media plane to reliably communicate with the lightning-fast control plane without forcing either side to wait for the other. When a viewer finally clicks play, their device sends a request to the API. Because the metadata cache was updated by the completion handler, it instantly returns the precise CDN URLs for the video. This diagram outlines the final delivery path. The actual streaming video payload is sent directly from the content delivery network, completely bypassing our core API infrastructure. Because the transcoder created multiple resolutions, the player uses adaptive bitrate streaming. If the viewer's network connection drops, the player instantly swaps to the lower resolution file, keeping the action moving without a single moment of buffering. But pushing all this data through global edge servers is incredibly expensive. We can optimize this because video views follow a long-tailed distribution. A tiny fraction of viral videos accounts for the vast majority of traffic, while most videos are rarely watched. This visual details our cost-saving routing strategy. We cache only the most popular videos on the expensive CDN edge servers. Less popular content is routed directly from our cheaper, high-capacity video storage. Smooth playback requires an intelligent global routing strategy. You minimize costs by reserving premium delivery networks strictly for high-demand traffic. Even with the media safely offloaded to the edge, the central database still faces extreme pressure. It must survive millions of heavy upload writes and billions of watch rates simultaneously. To survive the massive write volume caused by new uploads, we use database sharding. We split the data horizontally across multiple servers, distributing the intense write traffic so no single machine is overwhelmed. Then, to handle the billions of outbound read requests, we use database replication. Each primary shard creates multiple identical copies of itself. These replicas absorb the traffic from viewers constantly pulling metadata to load their feeds. There is a trade-off to this approach. Because data takes time to copy from the primary shard to the replicas, there is a brief synchronization lag. A newly uploaded video might take a few moments to appear consistently across different geographic regions. This split approach secures the system's brain. We shard the database to survive write-heavy uploads, and we replicate it to guarantee high availability for read-heavy playback. Because this architecture is highly decoupled, it naturally absorbs hardware failures. If a transcoding worker dies mid-job, the message safely remains in the queue, waiting for another healthy server to process it. Every component has a singular focus. The APIs orchestrate the logic. Object storage secures the bytes. The DAG workers process the media, and the CDNs deliver it globally. By obsessively enforcing a strict separation between the control plane and the media plane, you create a system capable of absorbing the heaviest files on the internet without dropping a single frame.